So, today, dear students, will start with this forced vibration due to base excitation. So, let me start writing. Uh, in many cases, the excitation of the system is through the support of the base. Support of the base. Okay. Instead of instead of being applied to the mass. The support is considered to be excited. Support is considered considered to be excited by a regular sinusoidal motion. Now let us assume that to be y is equal to capital Y sine omega t. Let this be equation 1. Now consider our system. Let's say we have a rigid support here. To the rigid support attached a spring having stiffness K, a damper having damping coefficient C. At the end, we have a mass attached to them. Let's say mass is M. Okay, and here we are considering the case of base excitation having a motion small y. The mass will have an amplitude of small x. We can write the same here. Consider a spring mass system where the mass is attached with the support by means of a spring of stiffness K and a damper of damping coefficient C. Okay. Now, considering absolute amplitude, okay, let x is the absolute motion of mass, absolute amplitude, we can say amplitude of motion of mass m. Now the equation of motion for the system may be written as mx double dot equal to minus c x dot minus y dot minus k x minus y. Okay. Assuming that the amplitude of motion of mass is greater than that of a base excitation. Okay. So we can rewrite this equation to uh, mx double dot plus cx dot plus kx, bringing all x component to one side, and on the other side we'll have all the y components, ky plus cy dot. Let this be equation 2. Now we have small y is equal to capital Y sine omega t from equation 1, we can see. So if you have a differentiation of this equation, we'll have y dot will be y omega cos omega t. Now substituting the uh, value of y and y dash in equation 2, we have mx double dot plus cx dot plus kx is equal to uh, k capital Y sin omega t plus c uh, y omega cos omega t, putting the value of y dot. Okay, so let us simplify this equation. We'll have r mx double dot plus cx dot plus kx is equal to, taking y common, we'll have k sin omega t plus c omega cos omega t. Okay. Or we can write this as y k square plus c omega square whole root over. We'll take a term outside. So inside we'll have k by divided by k square plus c omega square whole root over sin omega t plus c omega k square plus c omega square whole root over cos omega t. Okay. Or we can write this as y k square plus c omega square whole root over into, now this term, okay, we can represent as cos alpha sin omega t plus this term as sin alpha cos omega t. Where we got this? If we have the stiffness in the x as k and the value c omega and the y, and let's say this angle is alpha, then this value will be k square plus c omega square whole root over, right? So from this angle we can see that the value of k divided by root over of k square plus c omega whole square is cos alpha, and the value of c omega divided by root over of k square plus c omega whole square root over is sin alpha. So we substitute these two values here, right? Now further we can say that uh, uh, where alpha is tan inverse of c omega by k, or this can also be written as tan inverse of 2 zeta omega by omega n. Okay. Uh, this is about the angle, and from the preceding equation we can write this as mx double dot plus cx dot plus kx is equal to capital Y root multiplied by root over of k square plus c omega square sin omega t plus alpha. So from this we got the value of alpha here, because we have this equation cos alpha dot sin omega t plus sin alpha cos omega t. So it becomes sin omega t plus alpha here, where the value of alpha is written here. So we can say this one is our equation 3, this is equation 4, right? Then equation 3, and equation 3 is same as that of the equation of motion for forced vibration. So with harmonic excitation, harmonic excitation. So what was our forced vibration equation? It was mx double dot plus cx dot plus kx is equal to f0 sin omega t, right? So therefore, right, therefore the steady state equation solution for equation 3 will be x equal to capital X sin omega t plus alpha minus 5. Okay. Let's say this is equation 5, where we can write, where this capital X is the steady state amplitude, steady state amplitude. Okay, so and this is equal to y multiplied by root over of k square plus c omega square divided by root over of k minus m omega square whole square plus c omega square. Okay. So why? Because this we had our previous equation as mm, x equal to f0 divided by k minus m omega square whole square plus c omega square whole root over. So instead of this f0 we have used this value. Okay. So in a dimensionless form, sorry, this is y. So in a dimensionless form, we have x by y, x by y, no, it is x, no, it is x. So x by y will come to the left hand side. So x by y is equal to 1 plus 2 zeta omega by omega n square whole root over divided by 1 minus omega by omega n square whole square plus 2 zeta omega by omega n square whole root over. Okay, let's say this is our equation 6. In a dimensionless form, the ratio of amplitude of vibration of the mass to the amplitude of vibration of the base is this equation 6. Now the angle phi, the phase lag, tan inverse of 2 zeta omega by omega n divided by 1 minus omega by omega n square. Okay. You can say this is equation 7. Now comparing equation 1 and 5, it can be seen that it can be seen that it can be seen that motion of mass lags that of the support through an angle phi minus alpha. Okay, the angle of lag will be equal to 2 zeta omega by omega n 1 minus omega n square, okay, minus tan inverse omega n. Okay, this is equation 8. It's the total angle of lag 5 minus alpha. Now equation 5, 6 and 8 completely define the absolute motion of mass m, of mass m, because of base excitation. Okay, because of base excitation. This condition is for the absolute amplitude. Now we consider relative amplitude. Okay, that is relative motion of mass with respect to the support when there is a base excitation. So for relative amplitude, let z is the relative motion of mass m with respect to the support, then we can say z is equal to x minus y, or we can say x equal to y plus z instead, right? The same. Now, we have the equation of motion. Equation of motion of mass for an absolute amplitude case. Amplitude case is uh, mx double dot plus cx dot plus kx is equal to ky plus cy dot. Now substituting the value of x, substituting the value of x in above equation, we'll have uh, m y double dot plus z double dot plus c y dot plus z dot plus k y plus z is equal to ky plus c y dot. Okay. Now we can rewrite this equation as m z double dot plus c z dot plus k z is equal to minus m y double dot. Okay, because this ky term and this cy dot term will be 0 when you come to the right hand side. Okay, let's say this is equation 9. Okay, Now the base is excited, you can say the base is excited by a regular sinusoidal equation y is equal to capital Y sin omega t, or you can say mm, y dot is equal to y omega cos omega t, y double dot is equal to minus y omega square sin omega t. Now substituting the value, of y double dot in equation 9, we have mz double dot plus cz dot plus kz is equal to m omega square y capital Y sin omega t, equation 10. Okay, now equation 10 is the same as that of equation of forced vibration with rotating unbalance. So you can write as m d square x by dt square plus c dx by dt plus kx is equal to m0 e omega square sin omega t. Okay, so with a solution as x is equal to m0 e omega square by k, this we have already solved. Okay. 1 minus m omega square by k plus c omega by k whole square whole root over. Therefore, the solution mm, in a dimensionless form can be represented as z by y is equal to omega by omega n square 1 minus omega by omega n square whole square plus 2 zeta omega by omega n square whole root over. Let this be equation 11. Okay. This is the ratio of amplitude, and the angle phi, that is the phase lag, will be tan inverse of 2 zeta omega by omega n 1 minus omega by omega n square. Okay. Equation 12. This is the case for a relative amplitude in a basic set. Now let us consider a example. Now let's say this the support of a spring mass system is vibrating with an amplitude of 5 centimeter and a frequency of you can say 1150 cycle per minute. Okay, if uh, the mass is 0.9 kg and spring stiffness is how much 1960 Newton per meter. Load per unit deflection is stiffness. Okay, that's 1 Newton per meter. Determine the amplitude of vibration. Determine the amplitude of vibration of mass. And next bit is amplitude what amplitude will result if a damping factor of uh, 0.2 zeta is 0.2 is included in the system. Now let us solve this. We have the given data. Mass is 0.9 kg. Y is given 5 mm. Spring stiffness K is 1960 Newton per meter. Okay, so we can have this omega as 1150 into 2 pi by 60, that is 120.3 radian per second, and the natural frequency omega n will be root over of k by m. So 1960 by 0.9 root over as 46.7 radian per second. Okay, then omega by omega n is 120.3 divided by 46.7, that is 2.58. Okay, now we have the equation of motion for the base excitation. Equation for base excitation for absolute amplitude can be written as x by y is equal to 1 plus 2 zeta omega by omega n square whole root over divided by 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square whole root over. Okay. So for zeta equal to 0, we can write this equation as x by 5 is equal to 1 by 1 minus 2.58 square. Okay. Zeta term will be neglected, this term will be 0. So it will be 1 by 0.565, or you can say x is 0.886. Okay, 0.886 mm, because y was in mm, 5 mm, so x will be 0.886 mm. Now for zeta equal to 0.2, we'll have x by 5 is equal to 1 plus 2 into 0.2, the value of zeta, into the ratio of omega by omega n. Okay, we can substitute directly here as 2.58. Okay, square whole root over divided by 1 minus 2.58 square whole square plus 2 into 0.2 into 2.58 square whole root over. So the value of x will be 1.25 mm for a value of zeta 0.2. Okay, now we'll be covering vibration isolation and transmissibility. Okay, vibration isolation and transmissibility. This is a very important term in vibration, forced vibration and transmissibility. Okay, so we can write in vibration systems many kind of vibrations. Vibrations are undesirable, and can be reduced can be reduced if not eliminated. If not eliminated. For example, the inertia force are developed in reciprocating engine. In reciprocating engine, unbalanced force produced in any rotating machine part in any rotating machine, etc. These vibrations should be isolated. You can write this. These vibrations should be isolated. Okay. From the foundation, so that the adjoining structure is not set into heavy vibration. Is not set into heavy vibrations. The effectiveness of isolation may be measured uh, in terms of the ratio of mm, force or motion transmitted to that in existence. Means basically it is the effectiveness is calculated by means of a ratio of, if at all we are considering the force, how much force is transmitted to the through the base and how much force in exist. Similarly, in motion case, how much motion is transmitted through the base through the isolation process and how much is left in existence. Okay, so the first type is called force isolation. Force isolation, and the second one is known as motion isolation. Motion isolation. Okay. So you can say the lesser the force or motion, the lesser the force or motion are transmitted, the greater is said to be the isolation. Said to be the isolation. Okay. For isolation purpose, different materials are used. Different materials are used. What are they? First is pads of rubber, generally used at the base of machine structures. Pads of rubber, then felt or cork, okay, or cork is used. Then metallic springs in some cases they are used. Metallic spring in some cases, okay, etc. So these are the materials used for vibration isolation. Okay. All these isolating materials are elastic and have good damping properties. Okay. So you can write all these isolating materials are elastic and have damping properties. Damping properties. Okay. So first we'll consider force transmissibility. Force transmissibility. Now, force transmissibility is defined as the ratio of force transmitted to the foundation, force transmitted to the foundation, okay, divided by force impressed on the system. Force impressed on the system. Okay. Now let us say you have a mass M supported by a spring of stiffness K and a damper, and other end is supported with a rigid end. The mass is having a displacement of x. This is the spring stiffness K. C is the damping coefficient. The force applied on the system is, let's say it is F0 sine omega t. Okay. Now we can write the same thing here. Consider a mass M supported the foundation on the foundation by means of an isolator having an equivalent stiffness and uh, damping coefficient damping coefficient coefficient of K and C respectively. Now, the system is excited by a force equal to F0 sine omega t. And the differential equation of motion is, for this particular case, mx double dot plus cx dot plus kx is equal to f0 sine omega t. Let this be equation 1. Now, assuming particular solution, of equation 1 as x equal to capital X sine omega t minus phi. Let's say this is equation 2. We'll have x dot will be omega x cos omega t minus phi, or you can say this is omega x sine omega t minus phi, okay, plus pi by 2. Okay. Let's say this is equation 3. Now, substituting the value of again if you differentiate this, we'll have x double dot as minus omega square x sine omega t minus phi from here. Okay, if you differentiate this omega x cos omega t minus phi, it will be minus omega square x sine omega t minus phi, or we can write this as omega square x sine omega t minus phi plus pi. Okay. Now, substituting the value of x, x dot and x double dot in equation 1, okay, we'll have m omega square capital X sine omega t minus phi plus pi, okay, plus c omega x sin omega t minus phi plus pi by 2 plus kx sin omega t minus phi is equal to f0 sin omega t. Okay, or we can write this as f0 sin omega t minus kx sin omega t minus phi minus c capital X c omega x sin omega t minus phi plus pi by 2 minus m omega square x sin omega t minus phi plus phi is equal to 0. Let this be equation 5. Now the total forces the total forces acting on the system are: one is the external excitation force, external excitation force, then we'll have the spring force, okay, then dashpot force, then we'll have the inertia force, okay, we'll have the inertia force. Out of these four forces, okay, out of these four forces, the spring force, uh, kx, and dashpot force, uh, c omega x are the two common forces, two common forces acting on the mass and on the foundation. Here you can see from the figure they are acting both on the mass and on the foundation, both the spring and the dashpot force, right? So you can write here, therefore the force transmitted to the foundation is the vector sum of these two forces. Okay. So the force transmitted FTR denoted by FTR is basically the vector sum of Kx and c omega x. So you can write kx square plus c omega x square whole root over. Okay. Graphically, if you represent this, let's say this is the displacement, and uh, let's say this is the spring force kx, this is the dashpot force c omega x, and the vector sum will be the force transmitted, that is FTR. From the vector diagram, now you can write this as x k square plus c omega square whole root over equation 6. Okay. From the vector diagram, to find the value of x, okay, and phi in equation 2, consider uh, a perpendicular triangle OAB. Okay. OAB means from this diagram, let's say this equation uh, 5. Okay, equation 5, if you represent graphically, you can represent this as we have the displacement x, okay, lags behind the force F0 through an angle phi, and this is omega t. Okay. Now draw a vector parallel to the displacement, right? That will be kx. Okay. Now from this origin O, let's say this origin O, drop a normal on that line. This will be, let's say, point B. This is A. Okay. And again from here, this component will be c omega x, and this will be your m omega square x. Hope you understand how we got this graph, because in the equation you can see uh, first is your mm, minus kx sin omega t minus phi, right? So the direction is minus, means it is opposite to the displacement. So it is this total from A to here. This is minus kx sin omega t minus phi. This is parallel to the displacement. Again, the c omega x component has plus pi by 2. So it will be normal to this. So this will be the line of c omega x. Again, the m omega square x component is plus pi. Okay, so this will be towards this direction. So we got this graphical representation, and this part basically is kx minus, don't important now, we consider for the timing it is OAB. Okay, so from the triangle we'll have f0 as kx minus m omega square x whole square plus c omega x square whole root over. Okay, or you can write this as x taking out will have k minus m omega square whole square plus c omega square whole root over. Okay, so the amplitude x will be f0 divided by k minus m omega square whole square plus c omega square whole root over. Okay, let this be equation 7, and the angle phi will be tan inverse of c omega divided by k minus m omega square. Okay, this will be equation 8. So now substituting the value of x in equation 6, we'll have the force transmissibility FTR will be equal to F0 k square plus c omega square whole root over divided by k minus m omega square whole square plus c omega square whole root over. Okay, this is equation 9. Now this is the force transmissibility equation. So force transmitted, sorry. So equation 9 can be represented as a dimensionless form. So transmissibility, we can say transmissibility TR is basically the force transmitted divided by the force impressed, which is equal to 1 plus 2 zeta omega by omega n square whole root over. Okay, divided by 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square root over. This is the transmissibility equation 10. Okay, so the angle through which the angle through which the transmitted force lacks the impressed force is the applied force is phi minus alpha. So where alpha is basically tan inverse of c omega x by kx, that is tan inverse of c omega by k. Okay, or you can say alpha is tan inverse of 2 zeta omega by omega n basically. Okay, and angle phi is tan inverse of 2 zeta omega by omega n divided by 1 minus omega by omega n square. Okay, this one is zeta. So the total phase lag phi minus alpha is basically tan inverse of 2 zeta omega by omega n divided by 1 minus omega by omega n square. This is for phi minus tan inverse of 2 zeta omega by omega n. This is for alpha. This is the total angle phase angle difference between the force impressed and between the force transmitted. Okay. Now coming to the motion transmissibility. Motion transmissibility. Uh, let's say we have a system like this. This is spring stiffness K. This is damper and the mass attached to it, okay, is M. This is K, damping coefficient C, amplitude of vibration Y, amplitude of vibration X. So we'll have X by Y will be 1 plus 2 zeta omega by omega n square root over divided by 1 minus omega by omega n square whole square plus 2 zeta omega by omega n square whole root over. This is, let's say, equation 12. Okay, the ratio of motion applied to the motion transmitted. Okay, and then the phase lag phi is given by tan inverse 2 zeta omega by omega n divided by 1 minus omega by omega n square. Okay, this is the phase lag. So the angle of lag, total angle of lag phi minus alpha will be equal to tan inverse of 2 zeta omega by omega n divided by 1 minus omega by omega n square minus tan inverse of 2 zeta omega by omega n, sorry, omega by omega n. Okay, this is equation 14. Now, what are the typical isolators? Typical isolators used are coil springs, then elastometers made of generally rubber and neoprene. Okay, then steel springs are also used. Steel springs in some cases. Then in some cases, pad mounts are also used. Okay, these are the isolators. Please go through book for details on this.